But right now, I'll introduce our speaker. Dr. Jennifer McIntosh is a professor in hydrology and atmospheric sciences at the University of Arizona. She does a variety of kinds of research, but for the last several years, as you'll see, she's been working with Pima County and others to better understand the hydrology of the Cienega Creek watershed and what, and try to shed light on some of the blind spots that have been left by others in the past, and look at how the mine might or might not impact the watershed, but more importantly, as she once described it to me, characterizing the watershed well before the mine, so you know what the mine's impacts are or are not. But with that, I'll defer to Dr. McIntosh, and she'll take it away.
Great, thanks, Tom. That was a nice introduction. Sets up my talk well. So hi to everybody online. Thanks for coming today. As Tom said, I'm going to give an overview of over 6 years of research now, mostly student-driven, that I'll highlight in my research group at the University of Arizona, all focused in the Cienega Creek watershed. I know I'm probably preaching to the choir, telling you why we should all care about the Cienega Creek watershed, but I noticed I've got several students from my class online, and so if you haven't heard about this place, it's one of the few places in southern Arizona that we still have intermittent and perennial streams. A beautiful picture shown here that's important for supporting all of the vegetation in the region as well as the wildlife, including several threatened and endangered species. Some of the portions of the watershed are protected, both including outstanding Arizona waters, as well as through areas protected by the county, like the Cienega Creek Nature Preserve that I'll highlight today, and the Las Cienegas National Conservation Area belonging to the BLM that I'll also talk about today. And so as Tom described, these areas, including other portions of the southern Arizona where you find surface water and shallow groundwater, are under from many different threats, including climate change, as well as development, such as groundwater pumping and mining. And in areas like this, there's often limited baseline data to know what state of the system is prior to those anthropogenic effects. And the scientific information that the group and others have provided, we hope will help to inform active management of these water resources. So I take you on a tour, kind of the history of how I got involved in these projects and really highlight the partners, especially the students. So if you aren't familiar with the Cienega Creek watershed, it's southeast of Tucson. And I got interested about 6 years ago when I was reading the local newspaper and hearing really polarized views about the environmental impacts, potential environmental impacts of the proposed copper mine. And as Tom described, I'm a hydrogeochemist, and a big part of my research is tracing the origin and flow paths and age of water in watersheds. So I thought I could apply some of my expertise to try to provide more understanding as well as baseline data for this important watershed local to one. So at about that time, I met Rachel Tucci, who was an undergraduate in our department, Hydrology and Atmospheric Sciences at U of A. She was working on her undergrad and wanted a senior thesis project. So the two of us went out to Davidson Canyon and sampled several homeowners' wells, which I want to especially thank for access to samples for this study. And on a shoestring, we started characterizing the groundwater in the Davidson Canyon area. Soon after, we met Jean Marie Haney and Guido Bodner, which set us up with some funding from the Nature Conservancy through a grant through the BLM. And we expanded research into the upper part of the Cienega Creek watershed, and especially want to thank Chris Eastow and Dave Murray, both for help with interpretation of data and access to sampling. And again, thank you to the residents as well in the upper part of the watershed. So not long after we started working in this watershed, we met Ron Tiller from ADQ and Andrew Soliwan from the Desert Botanical Gardens, just serendipitously at one of these meetings, the Science on the Sonoyta Plain meeting. And come to find out, Ron and Andrew were also passionately working in this watershed on a shoestring budget on their own time on the weekends, coming out to collect water isotope samples of surface waters, which I'll talk more about, as well as setting up infrastructure that we could take advantage of. So we've teamed up over the years to do this kind of research. And Ron and Andrew and I worked closely with a master's student in my group, Erin Gray, and I'll talk about her work today. So more recently, my research group has been working in the lower part of the Cienega Creek watershed and Davidson Canyon, and this is through funding from the Pima County Regional Flood Control District. I want to especially thank the directors, Suzanne Shields, Jennifer Becker, David Scalero, and Frank Pastillion, who really have made this project possible, also provided their expertise and interpretation of the data. And so this more recent work has been driven by 3 additional students in my group. So Nicole Weber, Alyssa Kirk, and most recently, Claire Tritz. And as I go through the presentation, I'll show you the citation to their theses. And so if you're interested in any of these results in more detail, I definitely want to point you to their master's theses, which are available through the U of A library. And also thank numerous undergraduate students that have been involved in this project. So for the last 6 years, our overall objective throughout the Cienega Creek watershed and to better understand the nature of the hydrologic connection between the Sand Mountains and the basin groundwater, as well as the wetlands, including springs, cienegas, and surface flows. To do this, trying to understand the seasonality and elevation of recharge of groundwater, how that groundwater flows across the basins, and there's relative transit time or age of that water. And then finally, what's the seasonal source of water to wetlands, as I described, including Cienega Creek and Davidson Canyon. And ultimately, the big picture goal of our research is improve understanding of both the hydrological processes in the watershed to help to support land management decisions, as well as Tom described, developing baseline data in case there are future pressures, including a proposed mine or even development and groundwater pumping. We could evaluate what those impacts would be if we know what the current state of the watershed is. So how do we do research? We go out and collect water samples, which I'll show you the types of samples in a minute. And we measure what we call field parameters. So the temperature, the pH, the electrical conductivity, and the dissolved oxygen. And then we bring those water samples back to the University of Arizona, and we measure all sorts of what we call natural tracers. So these are things that are naturally dissolved in the water that come from the atmosphere when that water is recharged, or are dissolved from the rocks and metals that the water interacts with along its flow, to be able to tell a history of that water. And then we take all of that data and we plug it into models, hydrochemical models, to be able to better constrain the system. So just showing you some pretty pictures of places we've been and the types of samples we collect. These are nice pictures of the cienegas in the Las Cienegas National Conservation Area and the Cienega Creek. We also collected from springs throughout the watershed. In addition, we collected samples from the shallow alluvial aquifers along Cienega Creek, and now I'm starting to do that along Davidson Canyon. And this is a picture of Andrew and Ron helping to collect a water sample from these nice network of piezometers that they installed and collecting our water samples. We also measured, as I mentioned, many homeowners' wells throughout the watershed. We also collected stock tank wells, windmills, as well as a few monitoring wells. So basically wherever we could get water samples of the subsurface. And finally, we've set up a network of precipitation collectors that go all the way from the top of the Santa Rita Mountains near Mount Hopkins down to the bottom of the basin. So what I want to highlight today is hopefully not all of the details, but just some of the key results from our research over the last 6 years. And again, to point you for the details to the students' theses. So I'm going to start in the upper part of the watershed where Rachel Tucci did her master's thesis work. Here, Rachel sampled groundwater wells going from as far up into the mountains as we could, down into the basin towards Empire Gulch Spring, as well as the upper part of Cienega Creek. In addition, we sampled springs throughout the area and then the shallow aquifer through those piezometers in the alluvium. In general, groundwater flows from the mountains across the basin towards Cienega Creek. So I want to take a step back and just show you conceptually how water gets from the mountains down into the basin. So the upper part of Cienega Creek Basin, it's an alluvial basin shown here just very schematically in yellow. And really there's a couple flow paths. The first is water flowing either from the mountain bedrock into the shallow alluvium and out into the basin. So this you could think of as being a place like the Sabino Canyon and Rito Creek coming out into the Tucson Basin. The other way that water gets out into the basin besides the alluvial washes is actually in the subsurface. And we call that diffuse mountain block recharge, shown in these open arrows here. And I'm going to show you in the upper part of the watershed, that's the dominant way that mountain block groundwater makes its way into the basin and eventually out into the creek. So I mentioned we have a whole spectrum of tools that we use. We call these natural tracers, again, because they come from the water. One of those is looking at the water stable isotopes. And Chris Eastow has worked on water stable isotopes in the Tucson Basin for his whole career and has established a lot of important paradigms that we can apply to the Cienega Creek watershed. And so this is a plot looking at the hydrogen isotopes of water versus the oxygen isotopes. And I'm not going to get down too far into the details and really try to focus today on the results. And so what Chris shows is that in general, throughout Southern Arizona, summer precipitation has a more positive value compared to winter precipitation. And we also see a difference in terms of the elevation of that precipitation and recharge. So higher elevation tends to plot above this line. Lower elevation tends to plot along the purple line within the Cienega Creek watershed. And that the wettest events, the ones that produce the most precipitation, are the ones that create the most recharge. So I'm going to show you our results from the upper part of the watershed, again from homeowners' wells, from piezometers in the alluvium near the creek, and from springs. And what we find is that water sources in the upper part of the basin primarily come from a mix of winter and summer precipitation. There's significant evaporation, which we would expect in shallow groundwater as well as in those surface waters like in the cienegas. And that in terms of elevation of recharge, it looks like most of the recharge is coming from the mountain front. And so that means it could be higher elevation water within the mountain coalescing and then coming into the basin primarily through diffuse mountain block recharge. Surprisingly, even out in the Cienega Creek Basin, we found groundwater that represented high elevation recharge. So it had a similar isotope signature to what Chris has measured in springs in the Santa Rita Mountains, as well as the top of the Santa Catalina Mountains. So we see that high elevation recharge in the basin groundwater throughout Cienega Creek Basin. Turning to the age of the water, we have a couple different techniques to determine the timing of recharge of the groundwater. And so the first one we look at is called tritium. Tritium came from nuclear weapons testing in the 1950s and 60s. And then we introduced all this tritium into the atmosphere. So if you find it in high concentrations in groundwater, that tells you that water was recharged since the 1950s. And we call that modern water or modern recharge. Tritium is still produced in the atmosphere today, although at lower levels than the nuclear weapons testing. And so if you find tritium, for example, that has concentrations from about 3.1 to 5.3, that's representative of modern precipitation. If you find very low tritium values, then it tells you that water is older or was recharged prior to the 1950s. And so now if we look at the tritium concentration of groundwater throughout the upper part of the Cienega Creek watershed, what we found is that tritium values were very low. Often they were below the detection limit, which suggests that widespread water was recharged prior to the 1950s, even up at the mountain front. And so this provides evidence that groundwater was from the mountains, but primarily through that diffuse subsurface recharge, and that it's taking a long time to make it across the basin. There was a few samples that had modern tritium, but they're really representative of stock ponds and anthropogenic influence. So now that we know that the groundwater throughout the upper part of the watershed is older than the 1950s, we need to use an older age tracer. And the most common one used, which we did in our study, is carbon-14 or radiocarbon. This is the same way that you go about dating bones, except now in groundwater, what we're dating is carbon dissolved in the water. And if we look at carbon-14 across the upper part of the watershed and we correct the carbon-14 ages, we come up with values that range from about 30 years to about 3,000 years up near the mountain front to the oldest groundwater that is found near Cienega Creek, but at depth. So this groundwater that's 15,000 to 27,000 years old is actually deep beneath a clay confining unit. So turning, and I'll come back to that clay confining unit in a minute. So if we turn now to look at the shallow water in the next creek, and we look at the Cienega and the creek itself in terms of the source of the water, I just wanted to highlight here again this awesome network that really Andrew Soliwan and Ron Tillett together mapping out the location of the Cienegas and installing these piezometers to enable us to sample. Greg Young did her master's looking in detail at the Cienega and the creek and looking at their seasonal variation. So I'm going to just show you what we found for the creek and the Cienegas throughout the year and not look at the seasonal differences just to save some time. So cation exchange is a really important process throughout the watershed because of that clay unit that is found kind of in the center of the upper part of the basin. And we can use the interaction of groundwater with that clay as a tracer of the flow paths or source of that water. So we look at cation exchange using the ratio of calcium to sodium because groundwater in general, up at the mountain front and within the mountain block, such as we find in Onyx Cave, for example, has a really high calcium to sodium ratio. And that's because that groundwater is interacted with carbonate rock like limestone and has a high ratio. But as you go down into the basin and you go further away from the mountain block, we see this trend of decreasing calcium to sodium. What that represents is this calcium-rich groundwater from limestone dissolution reacting with clay and exchanging the calcium for sodium. So groundwater out in the basin and near Cienega Creek is more enriched in sodium than calcium. And this is something that was studied by Hans Huth in a chemical model years ago that we're confirming here in this study. If we turn now to the shallow alluvium and say, where is that water coming from? What we discover using many different tracers, including calcium to sodium, we show that the chemistry of that shallow groundwater is identical to the basin groundwater. And if we go a step further and we look at the springs, we see that the springs are also very similar to that shallow groundwater, which is suggesting that they have a similar source. And there is variability, and I'm not going to talk about that. It's related to summer monsoon precipitation. And finally, if we look at Upper Cienega Creek itself, what we see is that a strong portion of the creek appears to be supplied by that basin groundwater and that shallow alluvium, which is then again all connected to the mountain block. So using tritium again as a tracer to figure out the source of water, or to confirm the source of water in Cienega Creek is coming from basin groundwater, we can look at tritium concentrations with distance from the mountain block. And again, what we find is we find the higher tritium up in the mountain block representing more modern recharge. We find the low values throughout the groundwater, throughout the basin. And now if we turn to the shallow alluvium, we see that it also has low tritium, which suggests it's old groundwater discharging into the shallow alluvium. And again, the springs look identical to the alluvium. And finally, Cienega Creek looks similar to this old basin groundwater. And of course, again, there is some variability, which suggests some input of modern precipitation, but the dominant source of water supporting both the shallow alluvium and the creek in the upper part of the watershed is this old basin groundwater. And interestingly, if you go downstream past the Narrows into the lower part of Cienega Creek, you see an uptick in tritium, which suggests a younger input of a younger source of water in the lower part of the watershed. So to summarize our results for the Cienega Creek watershed, Rachel Pettucci put together this nice conceptual model that shows groundwater coming from the mountain block, interacting with and flowing through these clay layers, which really slows down the flow of water, and likely why we have such old groundwater in the upper part of the watershed. And then finally, the discharge of that old groundwater into the alluvium, which support Cienega Creek, as well as the springs and the wetlands adjacent to the creek. And again, that groundwater is coming primarily, it looks like, from diffuse or subsurface mountain block recharge. And we think the reason why there's not a lot of local recharge down in the basin is because of high evapotranspiration across the basin that's impeding recharge of local groundwater. So to add an implication, because Cienega Creek and the shallow groundwater and springs and cienegas are dependent on basin groundwater in a process that captures that basin groundwater either before it recharges the basin, so captures it up in the mountain block, or any process such as development and local groundwater pumping out in the basin, anything that lowers that regional water table could impact the amount of water that's able to discharge into these wetlands in the upper part of the watershed. So moving to the lower part of Cienega Creek watershed and Davidson Canyon, I mentioned that this has been more the focus of our recent research working with the Pima County Regional Flood Control District. This research was first really started by Nicole Weber, who did her master's thesis in this area. And this map is meant to represent not so much the details, but to show you the fact that we've got a pretty dense data set now from my group of sampling groundwaters throughout the area, as well as sampling surface waters. And we're now beginning to sample alluvial groundwater in the region. And we combine that data with previous data from the Rosemont mine, through and Hud Bay, through the environmental impact statement, where you're able to get all of their chemistry and isotope data. So similar to the upper part of the watershed, one of the first tools we apply is to look at the age of the groundwater throughout this part of the watershed. And just like we did in the upper Cienega Creek, we used tritium here to try to identify water that's been recently recharged that either carries that bomb tritium signal from the 1950s and 60s and or still contains tritium from natural atmospheric production today, versus groundwater that has no tritium, which would be recharged prior to the 1950s. And so this is showing you a map of the tritium concentrations, and the larger the circle, the higher the tritium concentration. So the first thing that we noticed in contrast to the upper part of the watershed is that there wasn't a clear spatial distribution in groundwater ages. We also found that even within a given area, like the Hilton Ranch Road area here in Davidson Canyon and the Empire Mountains, there's a large mix between both modern as well as pre-modern groundwater. And I think conceptually, one of the reasons for this is that Davidson Canyon is still really up in the mountain block. And when you look at cross sections of this area, the alluvium is relatively thin. So most of these wells are actually in the bedrock, which is different from the upper part of the watershed, where what we were sampling was really the basin fill aquifer system. And again, we see, rather than the really old ages along upper Cienega Creek, we see some input of relatively new groundwater along to lower Cienega Creek here, identified by the higher tritium values. We also did carbon-14 to capture those older groundwater ages, and carbon-14 can date things between about 500 to about 50,000 years old. And what we found in the Davidson Canyon area, again, was a real mix from water that appears to be modern in age to the oldest groundwater we dated was about 22,000 years old. In the lower Cienega Creek, the groundwater that we dated with carbon-14 ranged between modern, so less than 500 years old, to about 760 years old. So similar to what I showed you for the upper part of the watershed, we also looked at the water stable isotopes to get an idea of both the elevation as well as the seasonality of recharge, and then the relationship between groundwater and surface water. So Chris Eastow and Wright recently published a paper actually including the Rosemont data from the Santa Rita Mountains. And what they found is that groundwater within that portion of the Santa Rita Mountains appears to be recharged from a mix of both winter and summer precipitation. And this is important to know the seasonality because that tells you something about, for example, the potential impacts from climate change, which are likely to change precipitation amounts for the different seasons. He also found that that groundwater was likely recharged at about the elevation of the proposed Rosemont mine, which is about 1,600 meters, and that there's widespread evaporation, which again is unsurprising in a semi-arid environment. He also found what appears to be ancient groundwater that has a much lower isotope signature and relatively old carbon-14 ages. So if we use this paradigm that Chris has established to look at our data, this is what we found. So Nicole Weber in her thesis, she focused in on lower Cienega Creek first and looked at how the creek compared to local groundwater sampled from wells that were proximal to the creek. And what she found is that it looks like the elevation of recharge is approximately equal to the mountain front, and that recharge is coming from both a mix of summer and winter, and that some of the samples are more summer dominated and some are more winter. But overall, the isotopic composition of the creek looks very similar to the local groundwater. If we turn to Davidson Canyon and we look at surface flows in Davidson Canyon and compare those to local groundwater that we've sampled in the area, Davidson Canyon, at least isotopically, looks similar to the groundwater. It looks like the elevation of recharge is approximately about the mountain front. And interestingly, there's a much larger range in the oxygen isotope values of the surface flows. And we can use that as a qualitative indicator that the age of surface flows in Davidson Canyon is younger than Cienega Creek because there's more variability, which is more representative of the variability you see in precipitation. So one more tool, we have a lot of tools in our analytical toolbox. We turn to carbon isotopes of dissolved inorganic carbon. And that's really useful because it tells you groundwater that's relatively close to the surface and still interacting with soil CO2 versus groundwater that's more isolated from the surface and is reacted extensively with carbonate minerals. We have a lot of carbonates in our watersheds. I just want to point out that we've got carbonate minerals both as bedded carbonate like limestone. We also have a lot of caliche in our soils. And so the dissolution of limestone or caliche causes this carbon isotope value to become more positive. I'll start with the groundwater, which are shown in the big circles. What we see throughout Davidson Canyon and Lower Cienega Creek is that there are groundwaters that look like they're very chemically evolved or isotopically evolved. So this means that groundwater that spent a relatively long time in the subsurface and has reacted with those carbonate minerals. And we call that process incongruent carbonate dissolution. And you can see that those are the groundwaters that are below the detection limit for tritium dating. So those were the waters recharged prior to the 1950s. I'm going to highlight Cienega Creek and Davidson Canyon. So if we look at Cienega Creek in yellow diamonds, what we see is again that they have contain detectable tritium. So that tells us that there's at least a component of those base flow that is coming from relatively modern precipitation. And it's mixing with older groundwater. Interestingly, again, Davidson Canyon has higher tritium than Cienega Creek. And from all the different parameters that we've looked at, including carbon isotopes, it suggests that Davidson Canyon is coming from primarily a shallower groundwater source than Cienega Creek. And I'll show you more evidence for that. So we can also use, I'm going to talk about sulfur isotopes in a second, but we can use the geology of the lower part of Cienega Creek watershed and Davidson Canyon, which is distinct, to be able to tell us about the source of the water. And again, how these two sources are different. So for example, in Davidson Canyon, there's pyrite, iron sulfide minerals throughout the upper part of the watershed. Where in lower Cienega Creek, it's ubiquitous that there's gypsum in the Pantano Formation. That's why lower Cienega Creek and the groundwater in that area have high sulfate concentrations from dissolution of gypsum. Well, we can see that signature of the geology picked up not only in the groundwater, but also in the creeks themselves. And so, for example, I'll start with the Davidson Canyon area. We can measure the sulfur isotopes of the dissolved sulfate in the water, as well as the oxygen isotopes of the sulfate. And we can do what's called a fingerprinting approach. So we can look at previous data where people already measured minerals that contain sulfur from different sources. So gypsum is different than pyrite. And then as well as compared to local precipitation. And we can overlay our data on this type of a plot and be able to determine where the sulfate came from. And so for the Davidson Canyon area, the groundwater seems to be a mixture of sulfate from precipitation and from pyrite, which makes sense given the local geology. And if you look at Davidson Canyon, it looks like it's getting primarily its sulfate from precipitation with a little bit from mixing with local groundwater that's oxidized pyrite. This is very different from what we see in lower Cienega Creek, which really carries that gypsum dissolution signature from the Pantano Formation. And there are a few samples that show mixing with precipitation, but dominantly the creek looks like the groundwater, which looks like the gypsum dissolution locally. So we take all of that data that we've collected from the field and from the lab, and we input it into hydrochemical models. So this was Alyssa's Kirk master's thesis that she just completed last summer. And I'm first going to show you the results from lower Cienega Creek. And I'm not going to get, again, I can't really dive into the details today. If you're interested, please refer to her thesis. So what she did is, again, she took all that data and she characterized representative groundwaters in the area that represented different types of groundwater, as well as the average precipitation composition, and in some cases, the shallow alluvium. And she input that into a model where she has that water reacting with the local bedrock geology. And so we input minerals that we know are in the watershed. And through that modeling, she's able to calculate what percentage of the water that's in lower Cienega Creek is coming from these different water sources. And so upstream of Davidson Canyon in lower Cienega Creek, the base flow appears to be dominated by regional groundwater with some input of recent precipitation. And these models are non-unique because you come up with multiple combinations of rocks and minerals and different in-member waters mixed together and reacting to output the stream base flow. And so that's why, for example, there's over 106 models that we produce, but the models converge on a common factor. And using other information from our studies, we're able to kind of pin down those models based on a prior knowledge. And so what she discovered, again, is for base flow in lower Cienega Creek, up to 80% of that water is being supplied by regional groundwater. And that up to about 29% is locally recharged groundwater from precipitation. Doing the same thing in the Davidson Canyon area, we look at surface flows. And what we discovered is that they're dominated by locally recharged groundwater, And by that, we mean the alluvial aquifer that was recharged by precipitation that has spent some time in the subsurface. And we know this because of the geochemistry of that water. And that it's up to, in some cases, 92% is that alluvial groundwater discharging into Davidson to support surface flows. But importantly, there is a component of regional groundwater coming from the bedrock aquifer that supplies Davidson Canyon. And depending on the model, it ranges between about 8 and 45%. And finally, if we turn back to Cienega Creek and we look at the creek downstream of the confluence with Davidson Canyon, and we look at the mixing of Davidson Canyon, either surface flows or often subsurface flows into the alluvium that support Cienega Creek, we found that lower Cienega Creek base flows was approximately a mixture of about 57% of Cienega Creek water and up to about 43% of Davidson Canyon. So this was from our modeling studies. And interestingly, this confirms what Pegg discovered many years ago using water stable isotopes, that Davidson Canyon contributes about 40% of the water in lower Cienega Creek beyond the confluence. So to wrap up, just a summary of some of our key findings from the lower Cienega Creek and Davidson Canyon. Claire Tritz, a current master's student working in the area, put together this nice conceptual model. So we found that the lower Cienega Creek is primarily sustained by basin groundwater that's regionally recharged, although there's substantial contributions from Davidson Canyon below the confluence. The groundwater is being recharged both in the summer and the winter, and that recent drought has decreased precipitation contributions, which we can see in our modeling as well as in some of the observations that we're making. And that interestingly confirms what folks like David Scalero has shown us all about decreased surface flows because of the mega drought we've been in for the last 15 years. So as you know, with the drought conditions, as you decrease the amount of precipitation, because that does contribute to surface flows, we decrease the amount of discharge. Looking at Davidson Canyon, we see that Davidson Canyon is primarily sourced from shallow alluvial groundwater that has been more recently recharged by local precipitation, both coming from winter and summer precipitation, although it does have some contribution from older, more regionally recharged groundwater emanating from the bedrock. And interesting, just a heads up on Claire's recent findings, which are still ongoing. Claire is extending our studies up into the Barrel Canyon area. And what she shows is that the contribution of precipitation decreases as you go downstream. So there's greater amount of precipitation contributing to surface flows in Barrel Canyon, a little bit less in Davidson Canyon, and then in Cienega Creek, it's almost entirely basin groundwater fed. So to wrap up, you know, what does this all mean, or how can it be used to help with water resources management? These are just a few ideas. One is that since lower Cienega Creek surface water base flows are sourced from basin groundwater, we suspect they'd be more sensitive to activities that would reduce the regional aquifer or the regional water table, such as development, which could lead to cones of depression from pumping. Any pumping near a stream, no matter the source of the water, could capture flows and could decrease base flow. And then we're already starting to see the effects of climate change from the reduced flows from the last 15 years of a mega drought. In Davidson Canyon, surface water base flows, because they are more dependent on local precipitation and recharge into the alluvium and then discharge into the creek, it's likely more sensitive to impacts from climate change, which is affecting the timing and amount of precipitation, as well as any activities that could alter the surface of the washes upstream that's affecting the alluvium, the alluvial aquifer. In addition, because we showed that there is some component of older regional groundwater from the mountain block contributing to Davidson Canyon, any activities to deplete the bedrock aquifer or pumping near the stream could impact Davidson Canyon. And finally, because Davidson Canyon has a significant portion of contribution to Cienega Creek. Any decreased flows in Davidson Canyon could impact Cienega Creek. And then just to remind you, in the upper part of the watershed, what we discovered is that the wetlands in the Las Cienegas National Conservation Area are almost entirely dependent on basin groundwater. So any activities that may impact the regional water table, for example, by development and local pumping or capture of water along its flow path to the creek and those cienegas, could impact the surface water. So to wrap up, I'll just give you a highlight of where we're headed. So we continue to work in this watershed through funding from the Pima County Regional Flood Control District. And I'm really excited to report that we are in the process of installing some really high resolution field equipment that's going to allow us to capture storm event flows, as well as better characterize that alluvial groundwater that's sustaining at least Davidson Canyon stream. And Claire Tritz, as part of her master's thesis, has been looking into more the seasonal variability and the storm event characteristics of Davidson and Lower Cienega Creek. And then finally, Andrew, Ron, and I recently started working with a master's student, Adam Stratman, up in the Canelo Hills Cienega Reserve, which I was excited to check out just a couple weekends ago, to do a similar study. Where is the water in the creek and the wetlands coming from? So thanks for listening. I'm absolutely happy to answer any questions.
Folks have any questions for Dr. McIntosh? Okay, I'll start out. So Jen, do you think there are any particular management implications to the fact that Davidson Canyon seems to be more dependent on sort of monsoon, storm runoff and precipitation versus both the upper and lower Cienega Creek, which seem more dependent on that regional groundwater?
It's a good question. I've been thinking about that, and I don't know if I can say what managers should do as far as, but I could say what you just described, what it's going to be more sensitive to. And so because precipitation, which again has spent some time in the subsurface, that alluvial aquifer is really important, and any variability in precipitation, such as, for example, with climate change, could impact Davidson. We could see that impact more quickly. Whereas in the upper part of the watershed, because it's dependent on basin groundwater that's taken thousands of years to make its way from the mountain block across the basin, we won't see that climate change signal for a long time. And that's consistent with there's been several recent studies on climate change impacts to groundwater. And so in that sense, it'll be more buffered, but the impacts may be more permanent.
There is a question in the chat. Any isotopic evidence of connections between Cienega Creek, Davidson Canyon, and the San Pedro Basin?
That's a good question. Not that we've been able to see. So, I mean, there is this idea in the Southwest of, I'm forgetting the term right now, but interbasin groundwater flow. And that would be the only way you could really get water across the mountains. But that's really rare to pick up that signal. And that's not something that I've seen in the San Pedro Basin or in the Cienega Creek watershed.
Okay. And then from Doug Duncan, if you're familiar, how do your results differ from the geohydro information in the Rosemont EIS?
That's a good question. I don't think that I've read the EIS a couple of times, and I think that the information we're providing is distinct in the sense that I don't think they go too far into interpreting the chemistry and isotope, and I may be wrong from my memory of that. Their work has been more on the modeling, and which Tom showed in the last meeting, of what the potential impacts from a modeling perspective might have. And I think our results are consistent or help to inform those models.
Yeah, I think that's right. I think that the Davidson Canyon result, that it's more dependent on sort of the storm flow, I don't know how much that was incorporated or not into their models. I don't sense that it really was. So,
and if I can jump in about that, my reading of the Rosemont interpretation of Davidson is that they think it's more, as you described, storm flow and direct precipitation. We don't have evidence for that.
yeah.
So we've even done studies of reacting precipitation with the alluvium, and you cannot get the same chemistry. So our results showed that the water has spent some time in the subsurface. So it's not direct precipitation. And that's important because the Rosemont models would suggest you're going to dry up Davidson, but the next time it rains, it'll be okay because you'll have flow. And we don't show that. We show that, again, it's coming from precipitation that has spent time in the alluvium. And so if you dry up the alluvium, then it will impact the stream.
Yeah, that's a very good insight, Jen. Thanks. Other questions? Oh, here we get one from Gita. Would it be fair to say that springs or other waters with older groundwater would be more buffered from climate change / drought than springs with younger water, or other factors that complicate that resilience conclusion?
Yeah, that's a great question, Gita. I'll try to make it short. There was a great modeling study kind of globally around the world that showed that aquifer systems with older groundwater are more buffered to climate change. So you could think about it took thousands of years for that water to move across the basin. So if you reduce the recharge in the mountain rock, you won't see that signal for thousands of years. However, because it took that long, it doesn't mean that you won't see that signal eventually. And they'll be potentially more permanently impacted by climate change. But because it's taken so long, you're a little bit more buffered. So we'll see a quicker impact on climate change in younger systems, as you're alluding to, shallower groundwater, younger systems.
Yeah, I think Greg, seems like Greg must have a question.
I put it in the chat, but I'll ask it. Being new to this and new to this area, what do you recommend I would read and others would read to bring myself and others to bring themselves up to speed on the current mega drought? So, help us understand that. Anything in particular out there that you recommend?
Honestly, I think that there's been some really good local news articles by Tony Davis and others. Tom might know. This is really more
certainly
Tom's
Tony
area.
I think Tony's articles are always a good primer because he manages to both give you the current story, but then he gives you the backstory as well.
And where does he publish?
He's in the Arizona Daily Star. So he's on the environment and water beat is the way I described it.
Thank you.
Yeah. Okay. Other questions?
There's a good question from Michelle.
Can I?
Yeah, how would results vary with significantly larger mountain formations and varying geology? And the chemical markers consistent. That's a really good question. And it's kind of $1 million question. I would say understanding mountain hydrology is, Tom's shaking his head, yes, it's very complex. And that's because mountain blocks, by the nature of how they're formed, they have complex geology. Even the Santa Catalina Mountains is a mixture of a lot of different geologies. So one example, maybe I'll point you to. So one size doesn't fit all. But Chris Eastow's recent paper with Wright was a really nice example of just even differences between the Rincon Mountains, the Santa Catalina Mountains, and the Santa Ritas on recharge mechanisms, both in terms of subsurface geology and kind of how water flows underground, but also even the surface. So he shows that the Rincons that have these, I forget what you call them, but a different topography collects summer storm water, which then can infiltrate in a different way. So I don't necessarily have an answer for you, except that you've pinged that it is complicated, which is true.
Yeah, I mean, we definitely see, and that paper by Chris is great because this variation in the geology just across southern Arizona leads to seemingly very different hydrologic conditions in the various mountain systems, with, you know, like the Huachucas having some very sustained perennial streams for short reaches, whereas the Catalina and Rincons tend to not have these perennial streams, at least not as prolific as they are on the Huachucas, just as one example. So, and I think AT had a question.
Can I talk?
Yes.
Yeah. Yeah, I don't know how this works, so pardon me. But is there, you know, we recently read in the paper where there was going to be some testing in the borough. We live in Southwest New Mexico, and we have a cienega on our property.
Mm-hmm.
And so, and the water comes from the Borough Mountains, and there's going to be these mineral tests that are being done there, as being proposed. And I'm just wondering, and I don't, I grasp about 20% of what Jennifer told us today, but I'm wondering, is there a way that I can have this presentation, that I can talk to a woman in town who deals with mining issues, and also maybe say something sensible in opposition to these tests? I don't quite, you know, as I listened to all this, I struggled, you know, why do I care? Why is this important to me? How can I use this material to do whatever it is I want? I mean, we're doing restoration here, and I guess I don't know, I don't really care. I don't know that I care where the water comes from, as long as there's water here. So, geez, have I exposed my ignorance?
I'll try to philosophically kind of answer that. You know, maybe a little bit of a sales pitch of why it's important to know where the water is coming from is if that water, you know, say it comes from a shallow source near the stream, then it might be more impacted by climate change. And maybe you want to focus on activities that would help for more infiltration of water. If your springs, your cienega is dependent on basin groundwater that came from the mountains and took thousands of years, then I'd be more worried about development activity that could decrease that basin groundwater, say through pumping activities. So it's more of a conservation tool, of a way to figure out, you know, where you should focus your management.
Yeah.
I don't know what they're planning to measure in your water, what the purpose of the study is. And that's what I would try to find out.
Well, they're looking for gold, copper, silver, and one other precious metal.
So it's mineral prospecting. So AT, the presentation today will be available on YouTube. I think Anna Marie put earlier in the chat our YouTube playlist. So all the past presentations have been recorded. This one has too, and it takes us a couple days, but it'll get posted to YouTube probably by the weekend or Monday at the latest. So
okay.
Yeah.
Well, so obviously these people, they go up and you know, it sounds really quite benign. You know, there's maybe 12 holes and they're only 2 inches apart, and they fill them back with concrete. But then they take that data and hopefully sell it to a mining company, who then comes in, and, you know, my attitude is God knows what.
Yeah, I mean, so right there's I think the mineral prospecting that's being proposed and to be executed, but you're right, you know, mines have significant long-term impacts in their regions, where environmentally and otherwise. Yeah.
Thank you.
Yeah. Okay. Well, thank you all for coming. I'll just note, next month, our speaker is going to be Scott Jones from the School of Natural Resources. He's a PhD candidate there at the university. And he'll be talking about mesquite grasslands and the intersection of nature and society. I think some of you probably have gotten Scott's survey about sort of grasslands and what people's views and aesthetics are. And I think you'll see some of those results in his presentation. So thank you all for coming, and have a good day. And thank you again, Jen, for a great presentation. So.
Sure, my pleasure. Thanks, everybody. Bye.
Yeah. Bye.